Picture a circle. Now inscribe a perfect equilateral triangle inside it, with vertices E, F, and G sitting right on the circumference. Now here's the fun part. At each vertex, draw a new circle with the same radius as the original. These three circles overlap in pairs, forming three beautiful petal-shaped regions. What is the total area of those three petals? Let's set up the problem carefully. Our original circle has center O and radius R. Since E, F, and G form an equilateral triangle inscribed in the circle, each side of the triangle has length R times the square root of 3. That's a standard result from the inscribed equilateral triangle. Each of the three new circles also has radius R, but their centers are at E, F, and G respectively. Before we dive in, here's a great chance to pause and try this yourself. You have three circles of radius R, each pair separated by a distance of R root 3. Can you find the area of each petal and then the total? Take a moment. I'll wait. Each petal is the intersection of two circles, sometimes called a lens. For two circles of equal radius ER, whose centers are a distance d apart, the lens area has a known formula. It's 2r squared times the arc cosine of d over 2r minus d over 2 times the square root of 4r squared minus d squared. Let's plug in our values. Here, r equals r and d equals r root 3. Substituting d equals r root 3, the argument of the arc cosine becomes r root 3 over 2r, which simplifies to root 3 over 2. And the arc cosine of root 3 over 2, that's just pi over 6. So the first term becomes 2r squared times pi over 6, which is pi r squared over 3. For the second term, 4r squared minus 3r squared gives r squared, whose square root is just r. So the second term is r root 3 over 2 times r, which is r squared root 3 over 2. Putting it together, each lens has area pi r squared over 3 minus r squared root 3 over 2. Now here's a subtle but important question. Do the three petals overlap each other? If they did, we couldn't just multiply by 3. Notice that the center O lies on all three circles, since it's exactly R away from each vertex. But it turns out that O is the only point common to all three circles. The triple intersection has 0 area, so we can safely multiply by 3 without any overcounting. And now the grand finale. The total petal area is simply 3 times the area of one lens. 3 times pi r squared over 3 minus r squared root 3 over 2. The 3 distributes beautifully. We get pi r squared minus 3r squared root 3 over 2. Or, factoring out r squared, the total area is r squared times the quantity pi minus 3 root 3 over 2. Clean, elegant, and entirely in terms of r. So, 3 circles, 3 petals, and 1 beautiful formula. What I love about this result is how the square root of 3 from the equilateral triangle dances with pi from the circular arcs. If you enjoyed this, hit subscribe for more visual math puzzles. See you next time.